Hello, y'all, and welcome back to my DP Chemistry curriculum. Today we're doing lesson 25, Reactivity 2.1.3. We're talking about limiting reactants, excess reactants, and theoretical yield. So we're going to be able to identify the limiting and excess reactants from given data, and we'll distinguish between theoretical yield and experimental yield, as well as calculate percent yield. So before we really get started, let's think back to an example I used in lesson 23 and 24 when we make pancakes. So we've been using a kind of chemical reaction with pancakes, 1 cup flour plus 2 eggs plus 1 cup milk makes 2 pancakes, which is a great reaction. But sometimes you're not using this exact ratio. Sometimes you don't have this exact ratio. You go through your pantry and you find that you only have a few ingredients. You have 4 cups flour, you have 10 eggs, just short of your dozen, and you have 4 cups milk. And you're going to have a party and you want to make as many pancakes as possible. Well, you look through it and you find that with your 4 cups flour, you can usually make double that because it's a 1 to 2 to 1 to 2. So you can make 8 pancakes. Your 10 eggs could lead you to 10 pancakes, and your 4 cups milk can also lead you to 8 pancakes, which means you can only really make 8 pancakes because your flour and your milk are limiting the amount you can make. These would be your limiting ingredients. So this often happens in chemical reactions. So in chemical reactions, we have limiting and excess reactants. So let's define each of these. Our limiting, and these are pretty much defined by what they are, limiting reactant, is the reactant that is fully used up. Furthermore, something special about the limiting reactant is that this is what will determine the quantity of product made. So when we saw in our previous reaction, our 4 flour determined we could make 8 pancakes. Our 4 cups milk determined we could make 8 pancakes. Our egg, which is excess, did not determine it. So our limiting reactants are what actually dictate our final product, not our excess. Furthermore, not only do they determine the quantity of product made, they can determine the amount of excess used. So going back to our previous example, 4 cups flour not only means 8 pancakes, but it would also, according to our ratio of 1 to 2, mean that we only need 8 eggs. Therefore, even though we have 10, we're only going to use 8. So our limiting tells us a lot more than just the product. It also tells us the amount of reactant we're going to use for each. All right, the less interesting reactant is going to be our excess. And our excess reactant is usually often found quite easily because it's the reactant left over. So if you take some zinc and you put it in hydrochloric acid, and after a while the reaction stops and there's still some zinc left in there, zinc is your excess. If you put it for a while, the zinc completely disappears, then that is going to be your limiting. We'll just show that really quickly. So we have some reaction of HCl and some zinc. And we have 2 ways this can go. So if we finish and we still have HCl, but zinc is gone, then HCl is our excess. Zinc is going to be our limiting because it's used up. If, on the other hand, we still have some zinc, but less maybe, then we know that, well, and this would be no HCl, it's all used up, so it's probably all like water and zinc chloride. We know that our zinc, on the other hand, is going to be our excess, and our HCl was limiting. So that's kind of what happens here. Now, how do we actually determine limiting reactant? There's a few different methods out there, but the way I'm going to be teaching you is exactly the way the textbook in Cognity will often teach you. So how to determine limiting reactant. And this is via stoichiometry or mole ratios. So this is going to be mathematically. Now, because we could just determine it via observation of before, but we can also determine it using actual mathematical tools and mole ratios. So step one is you want to calculate the moles of each reactant. We went over how to calculate moles in a lot of detail in the last lesson. Then we are going to divide the moles of each by their coefficient in the balanced equation or balanced chemical reaction. So that's going to help normalize it. Normalize just means bring it to the same value, same base. And then we just look at the values. The smallest value is limiting. And the fun little extra about this is that we are going to use that limiting reactant to calculate quantities of all products made and all reactants consumed. So the way to best go through this whole process is to actually do it. So we're going to do a very long form question going into how to calculate limiting excess and how to actually use that. So let's do some big practice problem. I'll set it up and then you can try and solve it yourself. So we're going to start with 10.0 grams of aluminum added to 50.0 centimeters cubed, and you probably can guess what I'm going to do that, of 0.100 mole decimeter cubed inverse of hydrochloric acid, HCl, to produce aqueous aluminum chloride and, oh, that and is a little high, and hydrogen gas. All right, so we have a couple missions here. Step one, write the balanced equation. Step two, find the limiting reactant. Three, calculate the mass of each product. And finally, four, find the amount of excess product, and we'll figure out whether we want that in grams or moles when we get there. All right. So if you think you can try this on your own, go for it. Otherwise, I'm going to get started right about now. So starting with number one, write the balance equation. Well, I see aluminum plus HCl reacts to form AlCl3 plus H2. Now, in addition to balancing this, I'm going to use state symbols. Aluminum is a metal, therefore it's solid unless it's mercury. HCl is hydrochloric acid. Now, we know because we're dealing with a molarity, this is dissolved in water. This is HCl in water, so therefore this is going to be aqueous. For aluminum chloride, the question states aqueous aluminum chloride, but we would still know that because it is an ionic compound in a water solution. And lastly, hydrogen is a gas. I know hydrogen is specifically H2 because it's diatomic. Remembering our diatomics are HOFIN, Cl, and Br, Hoffenberkel. So there's my equation. Now I just have to balance it. So I'm going to use my balancing technique. I'm going to write each thing, Al, H, and Cl. For aluminum, I have 1 and 1. Hydrogen, I have 1 and 2. Chlorine, I have 1 and 3. So aluminum's good, so I don't have to worry about it. Hydrogen, I'm going to multiply by 2, and that's going to balance that out. Chlorine, I have to multiply by 3. Or sorry, actually, let's go through this. When I multiply that by 2, this chlorine becomes a 2. So the issue is I now need to multiply Cl by 2/3. This doesn't really work because once I change that Cl, it will also change this 2. So something that I may want to do is noticing that I have an even number here, which means I'm going to need an even number of hydrogen. However, chlorine is even and this chlorine is odd. What I'm actually going to do is start this whole process over, but I'm going to start by multiplying, and this may seem counterintuitive, the aluminum chloride by 2. This is going to set this chlorine value here to an even value. So I'm going to set this chlorine to 6 now. This aluminum is going to be set to 2. So I can correct that by multiplying by 2 over here. So I have 2Al. That's fine. And hydrogen now has to contend with chlorine as well. So I'm going to multiply this chlorine down here by 6, bringing this hydrogen to 6. Therefore, I must multiply this by 3 to get 6. So a lot of balancing is often guessing and checking. There's a lot of different ways to do it. Again, I linked that video in a different one, but just keep trying and practicing balancing is the best way to get better. So anyways, that is step one. We have our balanced chemical equation. We have state symbols. And we are able to deduce it from the given instructions. All right, step two, and I'll alternate colors. Find the limiting reactant. So for aluminum, we have 10.0 grams of aluminum. I'm going to convert that to moles using molar mass because we want to find moles. Grams on the bottom, mole on top. Now, I know from my periodic table that 1 mole of aluminum is 26.98 grams. So that's a relative atomic mass found on my periodic table. Using dimensional analysis, grams cancels out, and I get 0.371 mole Al. I'm going to divide this value by the coefficient for aluminum, which is 2, to get a grand total of 0.161 mole Al. So what I'm doing is following my instructions up here. Calculate the moles of each reactant and then divide by their coefficient. For hydrochloric acid, it's a little more difficult. For HCl, we need to use Mole is equal to concentration times volume. In this case, our concentration is 0.100 mole decimeter cubed inverse times the volume, which I'm already converting to decimeters, 0.500 decimeters cubed. You'll remember that if we have centimeters cubed, we must convert to decimeters by just moving the decimal over 3 places. In other words, we're dividing by 1,000. That mole value is 0.000800 mole HCl. We will then divide that value by the coefficient of 6 to get, or sorry, I've got this backwards. It's 0.00500 divided by 6 to get 0.0080. I'm missing some zeros. Let me just go ahead and correct this really quickly. 0.005 moles, and dividing that by 6 gets 0.0008 mole HCl. So going to step 3 in how to determine limiting. Step 3 says that the smallest value is limiting. Therefore, to determine which is limiting, I look at my 2 mole values and identify that hydrochloric acid is limiting. So HCl is limiting. All right, moving to number 3, we want to find the mass of each product. So I'm going to use my HCl value, 0.000800 mole HCl, and I'm going to find the mass of each of my products, starting with that. Now, the way I'm going to do this is convert moles of HCl to mole of product, convert that to gram of product. So with that, starting with my mole of HCl, I'm going to use the mole ratio, mole HCl to mole aluminum chloride. And looking at my balanced chemical reaction, my ratio is 6 HCl to 2 aluminum chloride. So 6 HCl to aluminum chloride. Then from mole of aluminum chloride to gram aluminum chloride. You might say, why are you writing aluminum chloride over and over? And it's to keep myself on track. Using my periodic table, I recognize 1 aluminum plus 3 chlorines is 133.34 grams per mole. That's a molar mass. Canceling my units, mole, 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 and I get a total mass of 0.222 grams aluminum chloride. So that's mass of one product. The mass of my other product, 0.00800 mole HCl. And very much like I did before, I have 6 mole HCl, but now I'm going to 3 mole H2. That 3 is coming from the mole ratio of my balanced chemical equation. Furthermore, 1 mole of H2 is 2.02 grams of H2. And that gives us, once we cancel all this out, mole with mole, mole with mole, that gives us a total mass of hydrogen produced of 0.00505 grams H2. Now, before we move any further, I realize I've made quite a massive mistake that you may have caught. I'm using the value not of moles, but of that limiting number. This should be the moles. These numbers still work out because I'm working from my notes I set aside for this, so I just can pull these equations right out off the top of my head. But the actual starting value should be your mole value. All right, so that is number 3. For number 4. Number 4, we're trying to find the amount of excess product. So what we're going to do is look at what we decided before. Furthermore, we can find all the amount of reactants consumed from our limiting reactant. What that means is these stoichiometric relationships that I used to find the products, I can repeat with our reactants. Starting with 0.005, and this is for aluminum, 00 mole HCl, I can convert that to mole of aluminum. And I'm going to still be using the same exact coefficients as before. The only difference is I'm going to a reactant, not a product. So 1 mole of aluminum weighs 26.98 grams, just like we mentioned before. Units will cancel. And we get a final mass of 0.4, sorry, 0.0450 grams Al. Now, specifically, this is the amount consumed in the reaction. Because this is the amount consumed, we take our initial amount, 10.0 grams aluminum, and we subtract 0.450 grams to get a total mass of 9.96 grams aluminum remaining. So it might be a little confusing, but our limiting reactant tells us how much we use. We only use this amount of aluminum. We started with this amount, so we just subtract the two to get our final answer. So that is limiting and excess. The final part of this lesson is theoretical and percent yield. I think I misspelled that. I think it's I before. I think it's, yeah, that looks better. Theoretical and percent yield. So what the heck does this mean? Well, theoretical yield is this is the calculated or maybe expected amount of product that can be made given starting conditions. So in our previous example, we have a theoretical yield of 0.222 grams of aluminum chloride and 0.00505 grams of hydrogen gas. Those are the theoretical amounts we could produce based on our original equation. However, in real labs, I'd like to use white for this. In real labs, these amounts are never made. You never make exactly what you want. If you do, you're a perfect lab scientist, but honestly, what it means is you probably made a mistake if you got the exact amount you expect. The reason for this is error. Error can be caused by quite a few different things. So one of the first is we have loss of product. So maybe you spilled some, maybe some evaporated. Maybe you didn't transfer it all from one container to another. Maybe you had trouble purifying it. There's many, many reasons for you to lose product. And it happens all the time. That would give you a smaller value. Maybe there's an incomplete reaction. So in an incomplete reaction, you don't turn all your HCl into hydrogen gas and aluminum chloride. Just some of it didn't react. Or maybe later on we'll learn about equilibrium, where maybe the reaction doesn't progress all the way to the end. That happens quite often too. Third thing is there could be alternate reactions. Maybe the aluminum reacted with oxygen, so there could be unexpected products. So if some of that aluminum reacted with oxygen and made aluminum oxide, there would be less aluminum chloride. And then lastly, maybe there's impure reactants. Maybe your HCl is not all HCl. Maybe there's another acid mixed in there. Or maybe your aluminum is not pure aluminum. Maybe it's a combination of aluminum and zinc. There's a lot of reasons that you would have this error that makes your expected yield not your actual yield. So the best way to do this is to work with an equation. But before we do, let's talk about what this is. So our percent yield, whoops, percent yield is quite easy to find. It is just your experimental yield. So this is what you got in the lab. This is what you found out, the actual real life yield that you got from your synthesis or whatever, over your theoretical yield, multiplied by 100 because it's a percent. Percents are always multiplied by 100 to get that value. And that's how you calculate it. So let's try an example. So let's take our previous reaction where we expect 0.222 grams of aluminum chloride. However, you did this, but you had to evaporate it to get the product. That's one of our purification techniques, separation techniques. After evaporation of solution and removal of excess aluminum, the product weighed 0.350 grams. Oh no, uh, that's a little high. Let's lower that. Let's say 320 grams. So the question is two parts. One, what is the percent yield? And two, what are possible reasons for this error? The IB is always going to ask you why. They don't just want to know what's wrong or how wrong it is. They want to know why it's wrong. That shows the critical thinking. The percent yield is the easy part. We just take our equation. Percent yield is equal to 0.320. That's our actual. Divided by 0.222. That's our theoretical, the one we calculated, times 100. And we get a percent yield of about 144%. That's okay. Our percent yield can be more, it can be less. It doesn't really matter. It just tells us that our actual product weighed about 1.5 what our product should have weighed. So that's our percent yield. Now, for 2, why is this wrong? Well, we have to figure out why would the mass be higher? Well, we noticed in the equation it said evaporation. But what if we didn't let it evaporate fully? A common error with evaporation is that people remove it before it's done evaporating and there's some leftover water. So one of the reasons is the product may still be damp, water not fully evaporated. Now, another issue that we can see is that we mixed with aluminum. The aluminum could have just been a bar of aluminum that was placed in there and removed when the reaction was done, or it could have been a powder that we had to sift out. Um, and there could be many other reasons. If it was powder, maybe we had to filter it. So maybe some of that got through. Another possible reason could also be that some solid aluminum was left behind. So these could be two possible reasons. Both of them will very likely give you points on a question like this. Anyways, this is all there is to percent yield and limiting in excess. Please take time to practice this skill. I hope it helped and have a great day.